So, part 2 of chapter 11 is about the ideal gas law. So, the ideal gas law equation is basically just a relationship between pressure, volume, and temperature, which we've done before, but now we're also adding number of moles. So, P is pressure. It must be in atmospheres still. V is volume. We want it in liters now. N is the number of moles. They're using N because lowercase m is used for mass. Capital R is a constant, 0.0821 liters times atmospheres divided by moles times Kelvin temperature, and then T is temperature in Kelvin. So the equation is PV equals nRT. So 5 variables, 4 which will be given to you, 1 which you'll be solving for. So very similar algebra to what you were doing in chapter 10. Okay, so let's just jump right into some examples. As I said before, if you actually try these out yourself, there can be no questions of how you're doing it. And if you do have questions, ask me. So what is the pressure exerted by 0.325 moles of hydrogen gas in a 4.08 liter container at 35 degrees Celsius? So however you want to set this up, I like to write it on the side. So I'm going to have P, V, N, R, and T. So what is the pressure? So I'm going to be solving for P in atmospheres. My volume is 4.08 liters. N is the number of moles. Remember, R is my constant. And I will not make you write the units for this. That's the only one. Okay? That's a constant. That's always going to be the same. And T, you have to convert it to Kelvin. So you add 273 to the Celsius. Okay, so those are my variables given to me in the problem. Here was temperature. Okay, R is not listed in the problem because R is a constant. So the equation is PV equals nRT. I am solving for P. So to get P by itself, I have to divide both sides by V. That will cancel out V. So P is equal to nRT over V. Okay, so there's 2 options when you're putting this into the calculator. And please pay attention because some of you just don't listen to how I tell you to put it in your calculator. You get the wrong answer. You either need to do N times R times T and then push the equal sign and then divide by V. Or you need to put parentheses around the top numbers, multiply together, and then you can hit the divide button. So it's up to you how you want to do it. Okay, so I'm going to do 0.325 moles times my constant R times my Kelvin temperature, all divided by my volume. So once again, in your calculator, either do 0.325 times 0.0821 times 298 equals, and then divide that by 4.08, or put parentheses and type it in your calculator with parentheses around the top and then the divide sign and bottom. Either one, doesn't matter. Okay, so once you solve that, I get that P is equivalent to about 1.22 atmospheres. 2 decimals, just like always, should be close to that because your numbers, you shouldn't be rounding terribly much. Okay? Just like with the gas laws, you can always check your answer by plugging your numbers back into this equation. The left side should always equal the right side or be very, very close to it. So you can always check your work. Okay, so nothing really new, just a different equation. Okay, try another. A sample that contains 4.38 moles of a gas, so 4.38 moles, that's N, at negative 23 degrees Celsius, that's T, I just have to convert it, has a pressure of 0.857 atm, that's P. What is the volume, V? Okay, so you can write that down the side if you'd like to. Try that problem out. I think you can do it by yourself. Pause the video, try it, and then I'll go over it. Okay, so the only thing you really have to convert here is you have to convert Celsius temperature. So negative 23 plus 273 will give you 250 Kelvin. Okay, so using my equation, PV equals nRT. Now I'm solving for V volume. To get V by itself, I have to divide both sides by P. That cancels it out. So V volume is going to be equal to nRT over P. Same as before. Watch how you put that in your calculator. So N was 4.35 moles. R is my constant, always the same number. T in Kelvin was 250. All divided by my pressure in atmospheres. Now, if you don't have pressure in atmospheres, you will have to convert it. Some of you forgot to do that on the last test. You have to have these specific units. All right, so the top multiplied together completely, divided by just the bottom, gives me a volume of about 104.9 liters. Okay, if you round it to 105, okay, but try not to overround. If I wanted this in milliliters, if the problem told you that, you would just have to convert to milliliters. Once again, you can plug all of your numbers back into the initial equation. The left side should be very much equivalent to the right side. Okay, so that's finding volume. What about finding temperature? So try this one out. Pause the video, try it out. Don't be lazy. If you can do these problems, you should be fine with the worksheets and eventually the test. Okay, so what temperature, T, I'm finding T, is required in order for 0.87 moles, that's N, of nitrogen gas to occupy 24.8 liters, that's V, at 4.5 atmospheres, that's P. Once again, if you weren't in these units, you must convert before you solve the problem. Okay, so using my ideal gas law equation, PV equals nRT, I am now solving for T. To get T by itself, I have to divide both sides by N and R. So I have that T is equal to PV divided by NR. Once again, throw some parentheses around it. You can't go wrong. So pressure times volume. I would throw parentheses around that and then hit the divide button. And then my mole number, throw some parentheses around your bottom numbers. Times R, my constant. So once again, can't stress it enough. I would put parentheses around those, hit the divide button, and then parentheses around those. You cannot get the wrong answer if you do it that way. So I have that T is going to be a big number, 1,571.83 Kelvin. Once again, plug it into your original equation. The right side should equal the left side to be very equivalent. So that is solving for T. If you guessed it, now we're going to be solving for N moles. So how many moles of chlorine gas is contained in 10 liters at 27 degrees Celsius and 3.5 atm? Only thing I have to convert is I have to change my temperature into Kelvin. So add 273. That gives us 300K. So once again, PV equals nRT. I am solving for n, so I have to divide both sides by r and t. Notice they're all capital letters except n. So n is equal to PV over RT. So pressure times volume. Why don't you put some parentheses around that in your calculator? Divided by my constant R times my Kelvin temperature. Okay? Moles, if you solve it correctly, should be about 1.42. Plug it into the initial equation. It should all work out. Okay, so those are obviously the simplest methods for solving. I'm just telling you to solve for a specific variable, and I've already given you everything in its correct unit except temperature. Remember, if it's not in atmospheres for pressure, you have to convert. If it's not in liters, you have to convert. Temperature, you're probably always going to have to convert because that's an easy conversion. And then R is always the same number. And that is the only variable that I don't mind if you leave off the unit. Okay, so using the same question as in example 7, or I guess it was example whatever for you, continue the work, but now solve for mass. So same exact problem we just did, okay? This is the exact same problem, except I'm saying what mass in grams. So pretended this was your question. Okay, you would have done the exact same thing. So you would have gotten this answer. And chlorine is diatomic. Don't forget that. Okay, now I have to make this into grams. How do you go from moles of one substance to grams of the same substance? You have to multiply by the molar mass. Okay, this is where some of you are going to kill yourselves with points. Chlorine is diatomic. There's 2 of them. Okay, so I have to do chlorine plus chlorine. So 35 about for chlorine, 35.45 times 2. Okay, there has to be 2 chlorines. If you put 35 there, you're going to mess up. So the molar mass goes on top. I just got this from the periodic table. This is the atomic mass, finding molar mass, and then 1 mole goes on the bottom always. Okay, so I would have solved the problem the exact same way I had to do just before this. I would have gotten moles of chlorine, but the problem asks me for grams. So now I just convert moles to grams. So 1.42 times 70 divided by 1. And now if I have my answer in grams, I get about 101 grams of chlorine, diatomic. Okay, so that's just one way I can make it a little bit more complex. Is instead of asking you for moles of a substance, I'm going to ask you for grams of a substance. Okay, so let's just try one full one where I'm specifically asking you to find for grams instead of just cutting it like I just did. Okay, so how many grams of carbon dioxide gas are there in 45.1 liters at 34 degrees Celsius and at 1.05 or 04 ATM? Okay, there is no mass in the ideal gas equation problem. So you would first have to solve for moles N and then convert it to grams. Okay, and changing my temperature to Kelvin. (307). Okay, so let's try this one out. So start the same way you would. PV equals nRT. Like I said, there's no M for mass, so you have to solve for N moles first. Divide both sides by RT. So PV, whoops, N is going to equal PV over RT. So pressure times volume. And this is why it's so important to actually try these problems, because if you're just watching me do them and you're not actually attempting them yourself in your calculator, if you're getting the wrong number, you're not going to know that until you get to a worksheet where it counts. So actually try these. Like I said, put parentheses around the top and bottom numbers. You're not going to get the wrong answer. You can't, unless you physically type something in wrong. Okay, so solving for N, which is moles, I get 1.86. Now I have to convert moles to grams because the problem says how many grams. Okay, first off, what is carbon dioxide? It's a prefix. You do not have to check the charges. So it's just 1 carbon and 2 oxygen, CO2, carbon dioxide. No checking of prefixes, or I'm sorry, no checking of charges. Okay, so 1.06 moles of carbon dioxide. What is the molar mass of carbon dioxide? Well, I have 1 carbon and 2 oxygen. Looking at my periodic table, the atomic mass of carbon is about 12. The atomic mass of oxygen is about 16. If you don't want to round, that's fine. If you are rounding, make sure you do so appropriately. So my total mass, molar mass for carbon dioxide is about 44. Okay, look at this unit, grams over moles. Watch this. 44 grams divided by moles. See how it's grams over moles? You don't want to write mole up here. Don't do that. Okay, moles on the bottom. So it's just gram on the top, mole on the bottom. Because you want moles to cancel out, you want to be left with grams. Okay, so once again, I solved for moles. That number has to be accurate to get the right final answer. If it's not accurate, go back and see how you plugged this into your calculator. 1.86 moles of carbon dioxide times the molar mass of 44 grams divided by 1 gives me 81.84 grams of carbon dioxide. Okay, so that's just one way to complicate it. Instead of asking for moles, I'm asking for grams. The only other way I could complicate just using this equation is, like I said, to have the units off and you would have to convert them first. So once again, that is just using the ideal gas law equation, PV equals nRT. Okay, there's a little bit of a way to complicate this. So you can actually use, and I know this looks like a lot on the slide, it's just because I don't have it popping up one by one. You can actually use the ideal gas law to find molar mass. Okay, so remember, let me get my highlighter. Molar mass is equal to moles divided by mass. Moles over grams, right? That's the, number of moles is equal to mass divided by molar mass. Okay, so we're saying that N in moles is equal to M mass divided by capital M molar mass. I do have some people that put molar mass as MM. I don't really care how you remember it, but just remember that MM is one variable. You're using it that way. Okay, so I'm starting here. N equals lowercase m divided by capital M. Now I'm going to say, instead of having N, PV equals nRT, okay, I'm going to take N and substitute this in, because I just said they're equivalent. So now, substituting that in, just think about it, reread it, re-listen to it. It's not as complicated as it looks. I would have PV equals mRT divided by capital M. All I did was take this N, nRT, and put this in it. Okay? So, that's just a lot of background information. I am then saying I want to solve for capital M. You would have to first multiply it up both sides and then you'd have to divide the N or the PV down. Like I said, a lot of fluff. Okay, just re-listen to that if you're confused. Here is what I need you to know right here. Just remember that. Capital M, molar mass, is equal to M in mass, grams, times R, which you already know, times T in temperature, divided by P and V. The only thing that's changed is I have substituted this N for this. Okay? I know it sounds very complicated, and if you're like, what the heck did she just do? Re-listen to it, reread it, or at least know this equation. It's just a different way of representing the ideal gas law. So with that being said, let's try a problem. If you're confused, I need you to focus on this equation. That's it. That's all I ask, especially because you're virtual. Okay, so what is the molar mass? I wanted a highlighter. There we go. What is the molar mass of a gas if 0.427 grams of the gas occupies a volume at 125 milliliters, 20 degrees Celsius, and 0.98 ATM? Okay, so we are using the rearranged version of the ideal gas law. So we're using M equals M, lowercase, RT over PV. This is what we're using. Okay, M is mass in grams, 0.427. R is still this exact same constant it was before. T is temperature, so 20 degrees Celsius plus 273 gives me 293 Kelvin. V is in milliliters. I need it in liters. Okay? So, to go from, I'm going to do it up here in the corner, 125 milliliters, because remember, 1 liter equals 1,000 milliliters. So I'm going to take 1 liter divided by 1,000 milliliters. So 125 divided by 1,000 gives you 0.125 liters. Okay? You should know how to do that. And then P is already in atmospheres. Oh, thank goodness. Okay. Because I'm solving for capital M, I don't need to rearrange the equation. I can just plug it in. Okay? So capital M is equal to mass times R times Kelvin T. I would throw some parentheses around there. Divided by P times V in liters. Throw some parentheses. Okay, so do the whole top divided by the whole bottom. I get my molar mass equal to 83.94. And what's the unit for molar mass? Grams over moles. Okay, so a little bit of a complex equation to actually get to this point. But once you know this, which is all I'm asking you to do right now, you just plug in the numbers. Just a different format. There is no moles anymore. Instead, we have mass. Okay, so finding molar mass. You can also use the equation to find density. Okay, so once again, just roll with me. Density is mass over volume. You know that. That's from like middle school. M over V. Okay, so now I'm saying, follow with me. I had this equation, okay? M over V, M over V, that equals D, okay? They're all the same thing. I am now saying I am going to replace M and V. I'm replacing this with D, right there, okay? Oops, I have so many colors going on, but that's okay. I just took D, bloop, and I put it in there. D RT divided by P. I'm saying that D was this, so I got rid of this. Okay? Now, I want to solve for D. Well, I would have to multiply P up. So PM, or MP, equals DRT. And then I would have to divide these down. Okay? Algebra. Once again, here is what I need you to know. Density D is equal to capital M, molar mass, times P pressure, divided by R the constant, and T temperature. If you did not follow me up until this point, at least know this equation. 3 equations you have to know. PV equals nRT, the original, to solve for molar mass. Capital M equals lowercase m RT divided by PV. And then this one, D density, is equal to capital MP divided by RT. We're just using different equations that are derived from the ideal gas law equation. Okay, so what is the density D of a sample of ammonia gas if the pressure is 0.928 atms and the temperature is 63 degrees Celsius? So I'm going to be using D equals MP over RT. So I'm finding D. Capital M is molar mass. I'll get back to that in a minute. Pressure P is given to me in the problem. R is still the exact same constant. T temperature has to be in Kelvin. So 63 degrees Celsius plus 273. All right, sorry guys, I had to pause it. I'm not sure where I left off. So, I was doing temperature. Okay, 63 Celsius plus 273 to convert to Kelvin gives us 336 Kelvin. Okay, so the only thing we don't know right now is molar mass. So ammonia, if you looked at your radical sheet, you would find that ammonia is NH3. Okay, so if I don't give it to you, you should be able to still figure that out. So NH3. So I have one N and 3 H's. Looking at my periodic table, nitrogen's atomic mass is about 14. Hydrogen's is about 1. If you don't want to round, that's fine. So doing the math, the molar mass of ammonia is 17. Okay, so just straight plugging it into the equation because we're solving for D density. Molar mass, capital M, times P pressure, and like I said, I would put parentheses if I was doing it in my calculator. I sort of kind of know what I'm doing, guys. You could take my advice. Times R the constant, or I'm sorry, divided by R the constant, and then Kelvin temperature, once again, I would throw some parentheses. Okay? Now, here's the confusing part. The units, actually, let me actually put the units in here. I want you to actually see how these units cancel out. So you're not like, where did she get those units from? Okay, so if you go back, R's units are liters times atmospheres divided by mole times Kelvin. Okay, I just want to throw that in there so you can kind of see where we're at. Okay, so if you were trying to figure out units, those cancel, and those cancel. You're going to be left with grams divided by liters. What is density? Mass over volume. So the units make sense. Okay, just so you understand where I'm getting the units from. All right, so throwing all that math in my calculator, I would get a density of about 0.57 grams over liters. That's how I got the grams over liters. All those units canceled out. Okay, so that is finding density. Once again, if this was complex for you, I at least need you to know this equation, and then you just plug it in. So I know I only did one example problem for each variable we were finding. If you think you would like more practice before you even start the worksheet, I can gladly either give you problems that I cut from this lecture to make it shorter as far as time-wise. I can even scan you and send you the problems worked out, whatever is going to help you. But I'm telling you right now, if you don't actually try these problems, you're going to struggle when you get to the graded worksheets. So please actually take your time walking through this, take some notes, try the problems, ask for help, and then start your worksheet so you're starting on the right foot. If you're already confused because you didn't do what you needed to do during this lecture, you're to blame for that. Okay? Please ask questions if you need it. That way you're successful on the next couple worksheets.